So let's pick up there. Let's see if we can work this problem a second way. Right, exact same problem, but this time we'll actually use variable specific heats this time. Okay? So if we do that, come on, give me ink. So we have the same scenario here, right? First law, it's the same problem, and you can see just above my tablet there, you can see the first law is still going to simplify down to the exit speed that we're looking for is going to equal the square root then of 2 times this h1 minus h2 plus v1 squared over 2. So that's still true. That's not going anywhere. The second law. The second law is still always going to be the change in entropy is going to be described by the amount of heat transfer that occurs per temperature plus the amount of entropy generated. Well, we're still saying these are both 0. Okay? So it's still isentropic. Little s2 minus little s1 is still equal to 0. But what we're going to do now is we're going to say, well, this is equal to s degree 2 minus s degree 1 minus r times the natural log of the ratio of pressures, P2 over P1. That's a little better. P2 is still not great. That's a little better. All right. So we're going to use this then. Okay, well, what we need to know then, so I'll set this aside. We'll use this kind of as a sheet then. And so this is or. Another way to do this. We're going to go look at properties now. So at T1 and the fact that it's air, the only thing I need to know for an ideal gas to find H1 and S degree 1. For an ideal gas, the only thing I need to know is the temperature. That'll give me the enthalpy and some other information. Not a whole lot, but some other information. So T1 being 1,000 Rankine. So this table, A17 in the back of your text is in Rankine. Now, I'm not going to try to put that on the screen. I'm going to assume that you can look it up on your own time. I'm going to tell you, though, that at 1,000 Rankine, H1 ends up being 240.98. And those are BTUs per pound mass. And then S degree 1, I do have a row for 1,000 here, 1,000 Rankine. Looks like S degree 1 is 0.75042. 0.75042. This is going to be BTUs for every pound mass Rankine. Okay? Now, what the heck are we going to do with that? Well, remember this expression right here. We're going to say that S degree 2 is equal to S degree 1 plus R Ln ratio of pressures P2 over P1. So that tells us then that S degree 2, based on our numbers here, right, 0.75042 plus, we had an R value back over here, R value of, we can go look that up, that is 0.06855. That's also BTUs per pound mass Rankine. That's going to get multiplied by the natural log of 12 over 60. And these are all BTUs per pound mass Rankine. So S degree 2 then, right, let's put this up here, let's see that. Let's do this. Let's do 12 divided by 50. I should have wrote this, or sorry, 12 divided by 60. I should have wrote this number down, so we don't have to find it every time, times 0.06855. Okay, that is this quantity here. Add to it 0.75042. So I'm getting here 0.6401 BTU per pound mass Rankine. Okay? So let's see where that puts us. So you can see here, 0.640 would be between these two rows. That puts us between 620 and 640, which is where we would expect. So that means our H is going to be between 150 and 153 and 148. So just kind of quickly there. So that means that H2 minus, we'll just write out the interpolation real quick here, minus 148.28 divided by 153.09 minus 148.28. So we're just going to crank this out real quick. So my S degree value of 0.6401 is between two other S degree values. 0.64, let's say 63395, 63395, and the other one 64159, 0.64159. So my S degree value is between these two, which show up on the table, which means my H value is going to be between these two. So it's going to be between 640 and 620 Rankine. That's what we expect from the last problem that we worked. Okay, so let's see if I can do this real quick here. So I'm going to do this ratio first. That's 0.6401 minus 0.63395 equals, divided by quantity, 0.64159 minus 0.63395. Okay, about 80%. That makes sense. We're closer to this one than we are that one. About 80% of the way to this one. Okay, and then multiply that by the difference of 153.09 minus 148.28, close parentheses, add to that 148.28. I do not expect you to do all of this algebra in your head and then translate it into a calculator. I've been doing this for years. It's very, very possible that I've made a mistake here, but I'm getting an H of about 152.15. That would be BTUs per pound mass. Alright, so what that does for us then, so we go back into this expression now. Now I've got both H values, and I've got H1 and I've got H2 to go back up here now. So now I can say for my first law that V2 is equal to the square root of 2 times H1. We looked up earlier, and so that's 240.98. 240.98 minus H2 we said is 152.15. Those are both BTUs per pound mass. We're good on time. My house is about to get loud. I've got to, the dogs are about to come in from outside. So if it gets a little loud, I apologize. This is 2537. Remember, we need this conversion factor. There's that many feet squared per second squared in every BTU per pound mass. And add to this that V1 squared over 2, that's 200 feet per second. That gets squared divided by 2. The whole thing gets multiplied by 2. Whole thing gets squared. Alright, let's see how we do. Make that negative, add to it 240.98 equals, multiply by 25037. Man, that looks real close to what we had earlier, doesn't it? Alright. Add to that this other term we said this guy is only 20,000, so add to that 20,000 that we found in the previous step, multiply by 2, take the square root, and there we are, V2, very close to what we got last time, about 21, we'll say 21.8 feet per second. I wouldn't argue at 21.9 too much. And it's right there on the edge of which way do we round that. Okay. 2 ways to work the same problem. The advantage here, notice I had to interpolate an H value because I had an S value that wasn't on the row. I got lucky, I didn't have to interpolate these. If I don't have a row for this temperature, I've got to interpolate both of these, and I probably have to interpolate this. I am doing guess and check all day if I've got to do it. As opposed to a bunch of interpolation, I'm doing guess and check every time. If I don't have to do much interpolation, this one's a good candidate as far as I'm concerned, because I can find both H1 and S degree 1, so I might actually use this method, use the variable specific heats using the S degree values. But either way works just fine. Be comfortable doing either one, right? And I'm perfectly fine. And because this is an isentropic ideal gas, there's actually even a special third way that you could do this problem. Add 2 minutes. Okay. Let me show you something. Okay. I normally am kind of cautious showing you this before you turn in the Chapter 7 homework, but given the compressed timeline, here we are. There's actually a third way. Some would argue this is the simplest way to do this problem. I wouldn't argue too much with that. This third way might be the easiest way to do it. Okay. You see these guys down here? Let me make sure we're on the screen. You see these guys? If I've got an isentropic process that's an ideal gas, isentropic process, I have these ratios. These are very powerful, but these are assuming a K average. Right? That's fun derivation. I don't have time to do the derivation, but let me show you this. Right? You can also say that T2 over T1 is equal to, close my text. I don't have these memorized, so give me a second, I'm going to look at them. I apologize. Okay, I can say T2 over T1 is equal to P1 over P2 to the power of K minus 1 over K. Now what is K? K is equal to C sub P over C sub D. That's a table property I can go look up. Now I'm out of time. You can do this, but you got to guess and check because you need a K average. You don't know T2, so you got to guess and check a K average. I got to go, guys. See you next time.